welcome back. So, in this lecture we are going to talk about trajectory based digital current mode control tuning and Matlab case study. So, this is the continuation of the previous lecture where we have reviewed or we have discussed about the large signal PI controller tuning in current mode control. In this lecture we will just summarize those results. Then we will talk about large signal tuning in digital current mode control and practical constant and with Matlab simulation case studies. So, if we recollect our large signal PI controller tuning in a buck converter. So, we have used this current mode control architecture and then we have used a normalized load feed forward, and then what we did was that in fact this gain is also that there is a outer voltage loop, and here we have considered H equal to 1. So, for our case we have considered, and the voltage loop is a PI controller in this case. And then we have discussed that Kp can be calculated as 2C by L delta I0 square root of V into Vq, where Vq equal to Vref for step up transient and Vin minus Vref during the step down transient. And the Ki is nothing but 2 pi MC plus M1 by 10 Vin, where Kn is the normalized gain, that is the feed forward gain. So, this is this one. Okay. Now, we want to see what happened. We have also discussed in the last class that this we have discussed this in lecture number 15 in our earlier course. But now we want to discuss if there is a limit in the controller gain, which that means we have calculated this optimal gain by analytical this calculation. But now if we want to limit this optimal gain, that means Kp equal to 20, suppose that is my practical constant that we have discussed, then how can we scale this other gain so that we can get the near optimal recovery? Because we have discussed in the last class that in fact we are going to discuss using Matlab case study. So, let us consider one scenario first. So, I just want to move to Matlab, and let us say for 12 volt input I am talking about a buck converter where inductor is 0.5 microhenry, capacitor is 220 microfarad, and we are talking about 500 kilohertz, and input voltage is 12 volt and output reference voltage is 1 volt. Now, if we apply a 20 ampere load step, then the Kp ideal gain can be calculated. If we evaluate, it is 107.775, which is pretty large, but we only have 20 is the upper limit. Suppose we want to constrain this gain into 20, then what to do? We have discussed that, So, Kp is the 20 is the upper limit, then what we will do? By taking Kp is 20, we have to find out the attenuation factor. So, we have to attenuate Kp, which is given 20, and what is the optimal gain that we have computed? We have to take the ratio and then we will get the attenuation factor. Then the integral gain has to be attenuated by the same quantity, and also this Kn, where is Kn? This Kn, and here also we are talking about Kn. So, here also we are talking about Kn, that means the current loop gain. That means this Kn will come as a Kn into I0 minus IL. So, that means if we normalize, if we reduce the gain, we have to reduce both the gain of the I0 as well as the inductor current. So, both inductor current and the load current will be the same scale because it is a buck converter. The average inductor current is equal to average load current. So, we have to find out, and we have discussed that this is because under sigma equal to 0, we can always normalize the switching surface. Now, once we derive this normalized gains Kn, K attenuation, in K integral gain, then we have to convert this into discrete time. So, proportional gain will remain same, and the integral gain will be multiplied by the time sampling time to get the discrete time integral gain. So, this is my discrete time integral gain. So, this is my discrete time integral gain, which is the continuous time integral gain into sampling time. Now we are talking about the mixed signal current mode control, where we want to implement our large signal tuning in the digital loop. That means our controller will be sitting in the digital controller here, and we have discussed this in the lecture number 15. But there will be a slight modification as per our requirement here. If we take this out here, that means we have this comparator, and this comparator negative terminal and this comparator positive terminal. So, negative terminal is coming out from the DAC, it is coming out DAC, and what is the DAC input? It is our controller GCZ, and the input is our error voltage in discrete domain. And what is this controller? We have discussed, this is like discrete time PI controller. Okay, so it is going out of the screen. So let us write once more. So it is discrete time PI controller. And as per our implementation, what we are going to do? We are considering one normalized gain Kn, then this is our inductor current which is added, and this is our load current which is subtracted. So, this is the modified representation, and we have discussed that if we scale down the proportional gain, because we need to consider the realistic or the practical constraint, then we need to attenuate also this feedback loop, and this Kn will be replaced by the attenuation factor that we have discussed in the previous slide. So, that means the mixed signal current mode control we have plugged in this digital controller Kp equal to 20, K attenuation factor we have discussed. For this there is a modification in this loop, and the integral gain it is in the continuous domain, and the discrete domain this controller gain will be set as this. And this part we will have to separately draw as if this will be your DAC, GCZ, and this part will be Kn will be there, this will be our IL, and this will be our I0. Okay. So, this is just a modification that we have to make. So, now we want to simulate this, okay, and we want to see what is the effect of sampling and how does it look like in the real Matlab implementation. So, in this case, if you know we are talking about again the same, because we have discussed this Matlab in week 3 in detail, where first we will clear the screen, we will take the buck converter parameter L equal to 0.5, all these things are given, 0.5 microhenry, C equal to 220 microfarad. We are initially talking about 12 input, but we can change it. Reference voltage we set it as a 1 volt. So, first we will load this buck converter parameter which I have just discussed here. Then we will set load resistance equal to 1, because if you go to the simulating block, we have a continuous load resistance here, and then we are applying a load step, current load step, and of 20 ampere. Okay. So, that means they are continuous load. We are not adding any RAM, but if you go here, there is a provision for RAM. You can actually subtract RAM, add with this or subtract with this. So, RAM we are not considering, so you can just drop it. So, this block can be directly connected here. Now, here the Kc, that means the current loop gain, which is a Kn we say, we can also use Kn here instead of avoid any confusion in the notation, and we have to accordingly set this is my Kn. So, there is no modulator gain, so we can, there is no point here. So, this part can be taken out. Input voltage we can change here whatever we want, we can change, whether we want 12 volt, whatever we can do. Sampling delay for the time being we are not considering, because if we consider sampling delay, then we will see. Now, we have a load current feed forward KFF. If you go here, there is a KFF, there is a load current feed forward tab. If it is 1, there is load current feed forward, and it is in the same scale of inductor current. We are running the simulation for 5 millisecond. At 3 millisecond, we are applying a load step of 20 ampere. Now, our practical gain is given as 20, that is given, suppose that is the upper limit, but the ideal gain is computed, and we have discussed earlier the ideal gain, if we calculate, it will be too large. That means we need to create an attenuation factor which will be 20 by 107.77. So, it will come around 0.18. Then what we have to do? The actual integral gain will be attenuation factor into the gain which is computed by our tuning formula, and the ideal proportional gain is also calculated using our tuning formula, and Kn, which is the normalized gain for the current loop consisting of inductor current minus load current, that is Kn. After all this, we have converted, and current loop is analog. So, proportional gain in discrete time is same as the continuous time proportional gain, and the discrete time integral gain is nothing but the continuous time integral gain into the sampling time, which is same as switching period, because we are taking one sample per cycle. Now, we want to run the simulation and see the effect. So, here we are considering 12 volt input, and now, and initially R was 1. So, if you go to the results, so initially if you consider the average inductor current was 1 ampere. So, because output voltage is 1 and load resistance is 1. So, if you go to the output voltage waveform, so output voltage is regulated to 1 volt more or less. Why it is slightly above 1 volt? Because we are taking the sample right here, because we are talking about digital control, it is not analog control, and we are taking one sample per cycle. So, if you want to see how does the sample look like, we can go to the plot and we can actually rerun this and show. That means, if we see the sample, that we are picking up sample right the valley voltage, which means we are regulating this sample voltage, not the full voltage, because it is digital control and we are getting one sample per cycle. That means, if you go all this waveform, you see we are taking the sample at every switching instant and which we are regulating. That means, once it slowly settle down, we are slowly settling down. So, this value is settling, which means we are settling the sample voltage, not the original output voltage. As a result, you can see there is a steady state error in the actual voltage, because, but if you take the sample somewhere here, then you will get. So, that we will discuss. So, first we have not, that means, in this case we have not considered any delay between the sample and the switching. You see the switching is happening at every this point and the sample is picked up at the same point. So, there is no delay considered here, but there is a delay due to the modulator, because if you talk about analog control, you see the switching is happening here. That means, if you take the one full cycle waveform, the switching is happening here, whereas the sample is picked up here. So, in analog control, till the switching happen, your output voltage will change and it will be reflected in the controller. So, the controller output will also get updated till the point of switching. But in case of digital control, the output voltage is locked. That means, your inside the digital controller only the red waveform will be available. That means, all this ripple information is lost, it is not reflected inside, you are only taking the sample. That is why there is a subtle difference between the point of sampling and the point of switching. The voltages are different, and that will cause a difference in the response between analog control and the digital control. And this delay actually will look like a delay, because there is a time difference between the sampling and the switching, and this will cause a delay. Okay. and because of this delay we will see. So, now we are talking about the inductor current ripple. So, you see it is not perfect time optimal control because, but it is fast enough, there is a in between switching, that is why we are calling it is not exactly time optimal, but we are trying to get close to the optimal response. Now, what happen if we decrease the input voltage? Instead of this, we decrease the input voltage to 6 volt and rerun the simulation. Now, we will see that if you take the output voltage waveform, there is a difference, there is a subtle difference, because here we are picking up the sample and there is a transient, there is a ESR jump, it is captured, but at the time of switching this voltage is used, where the actual output voltage gone far below, like 0.9 volt. So, in case of analog control, this output voltage will be reflected in the controller output continuously, but in digital control you are not taking into account this. So, that means one way to overcome, you have to increase the sampling rate in order to get faster recovery, because otherwise this delay is a huge delay and that is causing an additional voltage overshoot using our tuning formula. That means the delay between, because why this delay has increased, because we are using a lower input voltage. That means if you go to the inductor current waveform, okay, let us compare this with the earlier case. That means we will hold on this value, sorry, we will hold on this value, and so this one, and now we will use 12 volt and we want to change the color. So, plot comment, that means there is a plot reference, so we will use dash line and let us do that. So, I want to show you two response, difference in two response. So, first if you go to the inductor current waveform, I will show you that there is a change in the duty ratio. So, that means the 12 volt will have a smaller duty ratio, as a result the on time is small, but 6 volt has a larger duty ratio, so on time is large. Now, next go to the output voltage waveform. If you see the output voltage waveform, the delay between switching under high input voltage, you see this is a sample voltage and this point is switching happening. So, it is not that much large, but in this case it is large and voltage is fast discharging, because your slope of the inductor current is slower. If you go to the inductor current waveform, you will find the slope of the inductor current is slower, because at high input voltage your rising slope is higher, because it is V in minus V0 by L, whereas for lower input voltage the slope is slower. As a result, the rate of discharge of the capacitor is faster for in case of the lower input voltage, and that is why even a slight increase in the delay will cause a huge undershoot, and that create a mismatch between the sample voltage and the switching voltage where the actual switching is taking place, and that is causing a mismatch, and that is actually resulting into a large overshoot into this. So, that means if we go back to our code, so if we want to make changes here 6 volt, so we want to just draw the plot and analyze that this is because of the delay, and during this delay time the rate of discharge of capacitor is made much faster, and that is causing the whole lot of issue. Then what can we do? One way, because you cannot do anything with the delay, but there is an additional overshoot. So, you need to increase the current loop gain, so that it will create some kind of damping, because if you consider the inductor current minus load current, which actually resemble capacitor current and which actually gives some information of the derivative of the output voltage. So, if you can increase this term, then the derivative action will come and it will add some phase boost, As a result, you can reduce some undershoot effect. So, that means instead of this attenuation factor in original derivation, we multiply 2 times, that means we increase this gain. In optimal sense it should have been this, but due to the delay as well as due to the modulator delay, it is causing a deviation, and that is actually resulting into additional overshoot. But now we have increased the gain in the current loop, so that it will give some phase boost action, and we want to see what will be the effect on top of this by changing the color. So, we will use maybe magenta color and see what is the effect. So, now we have used a sort of similar to phase boost and want to see what is its effect on the transient response, whether can you reduce the current the overshoot, the additional overshoot can you reduce or not, that is what is the objective. So, now let us go back and see the magenta color. So, the magenta color is able to reduce the effect, that means if we go to the inductor current waveform. So, you see the magenta color has reduced the current overshoot, because we have introduced something similar to phase boost, and that is also obvious here. So, you can clearly see between these two colors. So, instead of magenta, let us use another color. So, maybe we can use black color, that will be much more visible. So, we will rerun this particular. Okay. So, now it is clear. So, the blue one was the response by using the optimal tuning gain, and that was giving additional voltage overshoot, but the black one is now the response by increasing the current loop gain from the optimal value, whatever we got we have increased, so that it gives a phase boost, but probably we have given excess phase boost, and that is why. So, now the third response you have to get, instead of 2 if we put 1.5, and now we rerun the simulation and we use a different color, let us say we will use cyan color and see what happened. So, here instead of 2 we have given 1.5. So, now using cyan color, it is somewhat better, it is somewhat close to the optimal, it is not exactly optimal, but somewhat close. If you go to the inductor current waveform, it is somewhat close to the optimal behavior. So, that means we can play with this gain by considering this sampling delay constraint, okay, and these parts are important characteristics. So, that means we will get if we go back to our thing, that means effect of sampling delay, what we saw, that this sampling delay effect, that effect is significant for higher duty ratio, or in other sense, or lower input voltage. And what was the cause? Because your delay amount was increasing, because what I am saying, that if you take the inductor current waveform in one case like this and another case, you have a smaller duty ratio. So, now we are talking about sampling point here. So, this to this delay. So, I am talking about this delay, and if you take this color, this to this delay. So, T2 and this is T1. So, T2 is larger, and not only that, this slope is smaller. So, it will causing more undershoot. So, as a result, the impact of undershoot will be more prominent. It is a cascading effect, both delay is increasing as well as the voltage rate of discharge is also increasing, and that is causing the whole lot of problem. So, then what is the solution? So, solution, one way to increase, we can increase current loop gain. That means we are talking about Kn, which is IL I0 minus IL feedback loop. So, for optimal we choose the K attenuation factor, that is for the optimal case, but now we will choose Kn maybe some 1.2 times K attenuation, that is to provide phase boost. Why we will say phase boost? Because this term, this IL minus I0 in a buck converter is nothing but the capacitor current. And what is capacitor current? It is C dVc dt or dV0 dt. Okay, so that means this is a derivative action, and if you take the Laplace, it is like a Cs, and if there is a, I would say, if there is a practical derivative action, then we will have a S tau d plus 1. We talked about this practical derivative gain in case of our PID controller. Now, this one, since this time constant is very small, the 0 is coming and that is giving an additional phase. That means the excess is coming as if, because it is a large signal model. So, there is no concept of frequency response phase plane, but if someone want to think in some sort of phase boost, phase lag, because that effect, that means if there is a lag, that means the delay will cause a phase lag and the phase lag will cause more oscillation or more overshoot undershoot. But if you want to reduce the phase lag, then you have to provide some additional phase boost, and that is actually is provided by this additional term. So, we need to amplify this factor. That means we need to provide. So, that means when you are increasing this term, that means we are increasing this particular action by one time. Okay. So, that means what was there, we are providing this. So, what I mean to say that this attenuation factor was coming from the optimal gain, because we want to make sure that practical gain constants are there. But in addition to that, we are giving some excess gain, so that we provide some phase boost, so that it try to anticipate whatever the phase lag happen due to the sampling delay. So, in summary, we have reviewed large signal PI controller tuning in current mode control. We have discussed large signal tuning, PI controller tuning in digital current mode control and their practical constraint. And we have considered Matlab case study, and we tried to cover what are the real time, what are the issues. That means when can you, because of the sampling delay, it can cause additional overshoot, undershoot. Then how to anticipate, some aspect are discussed, but more aspect will be discussed when we will do harder implementation in future. That is it for today. Thank you very much.